Okay, so let's do some practice with our electric field stuff that we've been looking at. And here we have a 0.18 Coulomb charge, which is 5.6 negative 12 kilograms in between two plates, 7.2 millimeters apart. And it goes across in 0.38 microseconds. And let's see if we can find out what is the strength of the electric field. Okay, well, let's look at some of the information we have here and piece things together. Now, one thing that sort of pops out to me right away here is I've got distance and I've got time. And with distance and time, I can calculate my average speed. So I'm just going to start with that. So my average speed would be distance over time. I've got my 7.2 millimeters. Of course, don't forget to change that into meters. And I'm going to divide that by the 0.38 microseconds. Of course, that's the -6. And I can get an average speed of about 1.89 times 10 to the 4 meters per second. So that's my average speed. So of course, what I'm going to do is I'm going to double that because it will start at rest, and then I'll have my change in V. So my change in V is going to be around 3.8 times 10 to the 4 meters per second. Okay, well, I've got change in V, and one of the logical things that we often find after that is acceleration. So we've got this, and let's find our acceleration. We have our change in V, we have our change in T, so we can take our 3.8 to the 4, and we can divide that by the T that we have from the beginning, and we can get an acceleration of around 9.97 times 10 to the 10 meters per second squared. All right, now I've got acceleration, and so far, average V, delta V, acceleration, these are all the exact same calculations you guys have been doing for a couple months already. And one of the next steps typically that we do is we find force. We've got the acceleration, we've got the mass, we can find force. F equals ma, no different than other stuff you guys have done. So I'll take that acceleration, I'll multiply that by my mass, which is already in kilograms, so that's perfect. And I multiply the two out, and it looks like we've got a force of about 0.56 newtons. Okay, now this is where the only newish type thing kicks in. You've got the force, you also have the charge, and electric field is electric force, which is what this is right there, divided by the Q. So I'll take that 0.56, I'll divide that by my 0.18 coulombs, and we've got an electric field of around 3.1 newtons per coulomb. And there we go. So that's how we can calculate the electric field. And literally, this is all stuff you guys have done before. The only thing that's different is that one calculation at the end. Everything else has been dTV, VAT, F equals ma, acceleration. It's all the same stuff, just a different scenario, a different application, and one slight different calculation at the end of this one, and that's it. Okay, combine that with a little bit of prefix action, and that's basically it. It's all pretty good. Okay, so let's do some more questions. Let's do some more examples. Okay, so here we have another scenario. This time we're going to use an electron, and the electron would go against the field, and it's between two plates 140 nanometers apart, and it hits going 0.70 C. Now, a lot of these particles go so fast, it's really common to compare their speed to the speed of light, which is what little tiny c means. So this thing is hitting going 0.70 C, or 0.7 times the speed of light. And of course, the speed of light is on your super sheet, and you should be able to find it there. And so first thing we'll do is convert this to meters per second. So we just multiply that by the speed of light. This converter would be around 2.1 times 10 to the 8 meters per second. Okay, now I'm not going to give you a question. We're not going to even have a question. We're just going to take this. Let's see what all the things that we can find, because that's a nice way to do some of these questions. Sometimes we're not sure what to do. Just start by finding stuff, and we've done that before. So this electron went 140 nanometers, and it hit the other side going 2.1 to the 8. So this would also be my change in V. Well, if that's my change in V, it's pretty easy to then take that and find my average V. I'll just cut that in half. So then I know that my average V is half of this, so 1.05 times 10 to the 8 meters per second. Okay, so I got my change in V and I've got my average V. Well, let's see what I can do with that. Well, I've got average V and I've got distance. With average V and distance, I can find time. So time is just distance divided by the average V. Now the distance is 140 nanometers. Of course, nano is another one of the prefixes. That's times 10 to the negative 9. Again, that's on your super sheet. So I got the 140 times 10 to the negative 9. I'm going to divide that by the 1.05 to the 8. So got the 140 to the power of negative 9 because it's nano. And we divide that by the 1.05 to the power of 8. It's going to be pretty quick here. We're looking around 1.33 times 10 to the negative 15 seconds. Okay, so I found time. Well, what could I do with this? Well, with time, well, I've got time and I've got change in V. Well, with time and change in V, I can find acceleration. So change in V over change in T, so I can take that 2.1 to the power of 8 that I found before. I'm going to divide that by the time I just found, which is 1.33 to the negative 15, and I can divide this two out, and I get about acceleration of 1.58 times 10 to the 23 meters per second squared. Okay, well, I got acceleration. Well, now what I could do, let's see, I know it's an electron, which means it's just an electron, so the mass and charge are constant. Those are things we know. They're on your super sheet. You can find the mass electron, charge electron. Well, if I know the mass, because it's an electron, I have the acceleration, I can find force. So force would be equal to mass times acceleration. Well, I've got the acceleration. I times that by the mass of the electron, which is 9.11 to the negative 31. And I can get my force on it. And my force would be about 1.44 times 10 to the negative 7 newtons. Okay, well, I've got force. Well, it's electron, so I also know the charge electron because that's also a constant. Well, with charge and force, I can find the electric field. Electric field would just be the electrical force, which is what that one is there, just divided by the charge of the electron, which is the E value. So I take that force, I divide that by the charge of the electron, and I get an E of about 9.0 times 10 to the 11 newtons per coulomb. And I got the electric field. See right there, without an actual question, I was able to solve absolutely everything about the situation just by using your basic stuff, the same type of stuff we worked on for a couple months. Change in V, average V, one thing leads to another. And eventually we solve for the entire situation without even giving you a question. And of course, the question could have been, what is the electric field? And to find that electric field, you would go through this process and find at the very end. Okay, so again, we got what? 1, 2, 3, 4, 5, 6 steps to the question. So as you can see, organization is really important. Labeling stuff is really, really important. But out of those 6 steps, the only one that was new or different was the very, very, very last one. The other 5 is stuff we've been doing a long time. So that's not too bad then. Okay, just the powers 10 a little bit different. Prefixes, you got to watch those. And the one slight difference for this one is given relative to the speed of light. But that you just switch into meters per second by multiplying by the speed of light in a vacuum, and you're good to go. Okay, well, let's try something else. I'm going to show you guys something else so we can keep on moving on with other types of questions. So before we get too much farther in other types of questions, we got to do some little bit of a subatomic review 101 type stuff here involving atomic mass and atomic number, because a lot of times we talk about using elements or certain nuclei and stuff like that in these types of questions. So it's good to practice some of the calculations that we need to be able to do in order actually to apply that. For example, what if we don't put a proton or an electron or something simple like that inside of parallel plates? What if we try and accelerate a nucleus instead? Like suppose it's a lithium nucleus, lithium 7-3, where of course the 7 is the atomic mass, the number 3 is the atomic number. And this kicks right back to grade 9 science when you learned about atomic structure and atomic mass, atomic number, and what that type of stuff represents. So of course the top number here, this is that's your atomic mass. And of course, the one below it, of course, is your atomic number. And if we go back to what these things actually represent, of course, the atomic mass tells you the number of protons and the number of neutrons put together. Okay, so there's 7 things in the nucleus, and of course the atomic number tells you the number of protons. And this is just basic grade 9 science. So lithium's got 7 things in the nucleus, 3 of them are protons, so 4 of them would be neutrons. Okay, so we have that. The other thing though is this gives us the mass in atomic mass units, or AMUs. But we can't use mass in AMUs, we use mass in kilograms, so we have to be able to convert that into kilograms. And if you look it up again, it's on your super sheet. 1 atomic mass unit is about 1.67 to the negative 27 kilograms. So we got to be able to convert that into kilograms, and we got to change the use the atomic number, how many protons, to figure out how much charge there actually is. So if we did that for lithium 7,3, suppose we got a lithium 7,3 nucleus. If we wanted to find the actual mass of this, we need to do 7 times the 1.67 negative 27, or times the value of 1 atomic mass unit, which is, again, on your super sheet. It's also approximately the mass of an electron or proton. So give or take, it's around 1.67 to the negative 27 kilograms for each one. So if we multiply that out, we can have the entire mass of the nucleus. Okay, so this is a really common calculation. It happens all the time for finding the masses of nuclei. So if we do that, we get approximately 1.17 times 10 to the negative 26 kilograms. And then for the other part, to find the charge of the nucleus, those are the protons. Of course, the protons are what give us the charge of the nucleus, and then we're just going to do 3 times the E value, or charge of electron slash proton, which we've been using already a little bit, so that's the 1.6 value. So we just take that and times it by 3, and we get a charge of 4.8 times 10 to the negative 19 coulombs. So that would be the charge of the nucleus. So it's really common, if you're going to use a nucleus, you have to be able to find the charge, find the mass, that type of stuff, if you're going to accelerate a nucleus and then do other calculations with it. A common one actually for this type of thing is what's called an alpha particle. And alpha particle is actually a helium nucleus, which is a common form of radiation, and it'd be helium-42. So if we wanted to get the charge of this one, it would be 4 times the 1.67 negative 27, because there's 4 things in the nucleus. So the mass for this one would be about 6.68 times 10 to the negative 27 kilograms. And the charge would be twice the charge of a proton, so around 3.2 times 10 to the negative 19 coulombs. So that's where we can use the atomic mass and atomic number in order to find the charges for these things and the masses. So then if we took quickly another one, let's take platinum, so that's PT, and we've got 195 and we've got 78. If we wanted to find the mass and charge of this one, well, to find the mass, we would have to do 195 times that 1.6-ish to the negative 27, and we'd have a mass of around 3.26 times 10 to the negative 25 kilograms. And for the charge, there's 78 protons, so we'll do 78 times the 1.6 value, or charge of a proton, and we multiply that out, and we get 1.25 times 10 to the negative 17 coulombs. So there's the charge of the nucleus. So this is a calculation that's it's pretty simple. It's just taking the value of 1 and multiplying either by the atomic mass or the atomic number, and finding out the masses and charges of different nuclei. So we don't just have to stick to protons and electrons. And it kicks back to basic grade 9 atomic structure, numbers and values with the atomic mass and the atomic number.